I'm excited to present to you the Gemini 2.5 technical report, which came out yesterday on June 17th. So to quickly highlight their abstract, they say that 2.5 Pro and 2.5 Flash are what they will focus on mainly. And they also talk about some features of the 2.0 series models. And of course, Gemini 2.5 is their most capable model. It can handle up to 3 hours of video context at once with state-of-the-art performance on frontier coding and reasoning benchmarks, whereas Gemini 2.5 Flash provides excellent reasoning abilities at a fraction of the cost and latency compared to previous models. Taken together, they talk about how they are essentially owning the Pareto frontier of model capability versus cost, which we will see in a graph somewhere in the middle of this video. So skipping the introduction, which doesn't really have that much content in it, the first thing worth noting is this nice comparison table of all of the Gemini models and their respective modalities, output modalities, output length, whether or not they reason, and whether or not they use tools and their knowledge cutoff date. So if you're into kind of seeing what the different models are and how they compare, then please pause and check this out. Next, we're going to move on to the model architecture. So I'm happy that they talk about the most important details in the first section after the introduction. The 2.5 series models use sparse mixture of extra transformers, of course, with native multimodal support for text, vision, and audio inputs. Sparse MOE models activate a subset of model parameters per input token by learning to dynamically route tokens via a router to a subset of R experts. And this allows them to decouple the total model capacity from computation serving cost per token, which is to say that you can kind of have free lunch in the sense that you have a pretty large model that you only refer to in a specific section based on the prompt. But despite the overwhelming success of sparse MOE transformers, they are known to suffer from training instabilities. So the Gemini 2.5 model series make considerable progress in enhancing large-scale training stability, signal propagation, and optimization dynamics, resulting in a considerable boost in performance straight out of pre-training compared to the previous Gemini series. One thing that I thought is pretty cool here is that they talk that with the 1 million context window size in terms of tokens, the Pro and Gemini 2.5 Flash models can process text such as Moby Dick or Don, I forget how to say this, Quixote, which are pretty long books, whole code bases, and long form audio and video data. As you remember, they said that you can watch or feed a 3-hour video into Gemini 2.5 Pro. Furthermore, architectural changes to Gemini 2.5 vision processing lead to a considerable improvement in image and video understanding capabilities, including being able to process what I just said, these long video formats. And looking at the Pareto frontier that they mentioned, they're essentially saying that they own all of the models which have the best cost versus latency, cost versus performance ratio. But what is worth noting is that they may have construed this data by using a 3-to-1 input to output token ratio. One thing worth noting is that output tokens cost more than input tokens. So maybe they made this ratio such that it favors their models particularly, and the price here is per million tokens on the bottom, and it is like slightly logarithmic and then linear. It's kind of weird. You can see that they have the grids like completely out of proportion, but I think that overall this is definitely showing that the 2.5 series is very advanced, but I also think that there's definitely some trickery going on here with how they're using the ratio in order to show them as being the best at everything, which of course is not the case. There are other competitors which have capable models. So we talked about the sparse MOE architecture for the 2.5 Pro series, but the smaller models in the Gemini 2.5 series, which is to say Flash, use distillation. And to reduce the cost associated with storing the teacher's next token prediction distribution, they approximate it using a k-sparse distribution over the vocabulary. So if you're not aware, in distillation, we're able to have a much more efficient and targeted training paradigm, because instead of having a binary signal, which is the case in normal LLM training of whether or not the LLM corrected the correct token that was in the training text, instead we can use a distribution from the teacher model in order to correct our student model's distribution. So not only can we say, did you correctly predict the next word, but what was your distribution compared to the teacher? However, what this means is that if we use the distribution over the entire vocabulary length, then for every single training instance, when we update our model through a forward-backward pass, we'll have to compare the entire vocabulary length distribution with the teacher and the student, which if you have like a 50,000, I'm not sure what the current size of vocabulary lengths are, but they're in the tens or even hundreds of thousands. That's a very large distribution to compare. So instead they use a k-sparse distribution, which is to say that if you have a 5-sparse distribution, you only compare the probabilities of the first 5 tokens predicted. So maybe one word had an 80% chance in the teacher model, another had a 3, 2, 1, and then 0.5. You only compare those 5 tokens between the teacher and the student. And it's worth noting that this still increases training data throughput and storage demands by a factor of k, because in the binary case, we just have 1. And if we compare 5 tokens, then we're multiplying it by 5. But they still find this to be a worthwhile trade-off, given the significant quality improvement distillation has on smaller models, leading to high-quality models with reduced shipment costs. And here I've just essentially rewritten what they have said in here, because the first time I read this paragraph, I didn't understand. So if you didn't understand my explanation, then feel free to read what I have added. When it comes to the data set, they use a large-scale, diverse collection of data encompassing a wide range of domains and modalities. So pretty standard stuff: web documents, code, images, audio, video. And the cutoff date, which was also in the table, is either 2025 or 2024, depending on the model version 2.0 or 2.5. And comparing to the 1.5 training data sets, we also utilize new methods for improving data quality, which is to say more improved filtering and deduplication. Furthermore, their post-training data set, like Gemini 1.5, consists of instruction fine-tuning data that is carefully collected and vetted, yada, yada, yada. And here they have a comparison with OpenAI, Claude, Grok, and DeepSeek based on the number of tokens per second while generating, so the throughput. Once again, Google may or may not have construed the data to show them at the top, because they're literally ahead of everybody in this graph. So take this with a grain of salt. Also, if you look at Cerebus or Grok, they have output tokens per second in the tens of thousands. Of course, those are much smaller models and much less capable, but this is just to show that in terms of output token throughput, it's more of just an engineering problem to optimize as opposed to a incredible innovation which improves model capacity. So I think that this graph is not that meaningful compared to others. And now let's look at the training infrastructure, which is really interesting. So the model family in 2.5 is the first to be trained on the TPU v5p architecture, which uses synchronous data parallel training to parallelize over multiple 8,960 chip pods of Google's TPU v5 accelerators distributed across multiple data centers. So I think this is pretty insane, because first of all, each pod has 8,960 chips. So if you compare this to a NVIDIA node, which has eight GPUs per node. Of course, a GPU has many chips inside of it. I don't know what the comparison is exactly, but this is still massive, and they're doing it across data centers. So this immediately makes me ask myself, how are they transferring between data centers at a fast enough bandwidth to facilitate training that isn't at a snail speed? Because communication is the largest bottleneck when you have to move weights and gradients, etc., between GPUs, or in this case TPUs. So they must have some pretty proprietary solutions in this regard to move data centers, or maybe they literally have a cable which is reserved for moving data between the data centers. I'm not sure. And then here they talk about the main advances in the software pre-training infrastructure. First of all, they have slice granularity elasticity, which seems pretty complex, but essentially it's just fault tolerance. So their system now automatically continues training with fewer slices of TPU chips when there's a localized failure. And at the scale that they're training on, localized failures happen every few hours. So this is inevitable. And this reconfiguration results in only approximately tens of seconds being lost during training time per interruption, compared with 10 or more minutes when waiting for healthy machines to be rescheduled without elasticity. Furthermore, the system continues training at around 97% throughput while the failed slice is recovering. So only a 3% drop in productivity for like 10 seconds. This is quite impressive at the scale that they're training on. And like I said, they have interruptions multiple times per hour, but the fault tolerance machinery is designed to tolerate the higher failure rates expected at these large scales. And then there's also split phase SDC detection. So SDC corresponds to silent data corruption, which just means if a GPU is still working, but is like doing complete garbage calculations. So this is a big problem because it can corrupt the data. And now they use lightweight deterministic replay to immediately repeat any steps with suspicious metrics and compare pre-device intermediate checksums to localize the root cause of any data corruption. And what this means empirically is that accelerators, if they start to exhibit intermediate SDCs, then they will be identified within a few minutes and quickly excluded from the job. During this run, the training run for the 2.5 series, around 0.25% of steps were replayed due to suspected silent data corruption. And of this 0.25%, 6% were actually hardware corruption. So that's a very high false positive rate of 94% being detected as superfluous. But because of the fact that this does ruin the training run in certain instances, it's good to redundantly replay a lot of extra training information if this can allow those silent data corrupted nodes to be detected. Something which I also learned is that they claim that these implementations were easy because they have a single controller design of the pathway system, which allows all accelerators to be coordinated from a single Python program with a global view of the system state. The controller can make use of parallel remote Python operations on TPU workers to monitor training metrics, track performance, stragglers, and root cause SDC errors. So in my mind, I picture some massive file management system with a lot of different scripts running for this massive GPU run on Google, but in essence, it's actually just one Python file. So that was quite hilarious to me when I read it for the first time, but I guess it makes it much more easier for them to manage. And in conclusion, 93.5% of the time during the run was spent performing valid TPU computations. The remainder was spent half in elastic reconfigurations and half in rare tail cases where elasticity failed. And then around 4.5% of the commute steps were replays or rollbacks, which are redundant for model debugging interventions. Here they have an impact of thinking on Gemini model's performance, which just shows that thinking helps linearly, if you're interested. Now moving on to post-training, they use SFT, reward modeling and reinforcement learning stages after the model has been pre-trained. And a key focus recently has been leveraging the model itself to assist in this process, enabling more efficient and nuanced quality control. And as has been the current trend, they also increase the training time compute allocated to reinforcement learning. And algorithmic changes to the RL process have also improved stability during longer training runs, because it is known that reinforcement learning is quite a fragile process where in the loss landscape, all of a sudden we can ruin the model weights. So this is important to have a stable training process. And these advancements have enabled Gemini 2.5 to learn for more diverse and complex reinforcement learning environments, including those requiring multi-step actions and tool use. Now, when it comes to thinking, they also added RL to the Gemini thinking models training to use additional compute at inference time in order to arrive at more correct answers. So this is essentially what DeepSeek did in their paper when they released R1. So Google pretty much is copying DeepSeek here. And the resulting models are able to spend tens of thousands of forward passes during a thinking stage before responding to a question or query. And they've moved from the Gemini 2.0 Flash, which was really only good at math, at code, at reasoning, to the 2.5 thinking theories, which is pretty much good at everything for reasoning. They also have this weird table, which I have no idea why it's been put in here, which just has the model IDs corresponding to their Google AI Studio API key, or not API key, but API like tag. So I guess if you want to look at these and memorize this table, then please be my guest. Now, moving on to the context length a bit, they integrate thinking into other Gemini capabilities, such as multimodal, and then once again, the long context, which exceed 1 million. And they also provide the ability to set a thinking budget in the API if you don't want to have costs balloon, which means that it will only say like you can think for 20,000 tokens, and then you have to stop and give the answer. Moving on to capability-specific improvements. Of course, code is the most important thing. That's why it's first. So in pre-training, they talk about intensifying their focus on incorporating a greater volume and diversity of code data from both repository and web sources into the training mixture. And this has, according to them, rapidly expanded coverage and enabled development of more compute-efficient models. And during post-training, they developed a new training technique incorporating reasoning capabilities and curated a diverse set of engineering tasks with the aim to equip Gemini with effective problem-solving skills crucial to addressing modern engineering challenges. Key applications of this are ID functionalities, code agent use cases for complex multi-step operations within full repositories, and multimodal interactive scenarios such as end-to-end web and mobile application development. These efforts have yielded a broad and significant improvement in Gemini's coding capabilities. Moving on to factuality, pretty much they're just saying that now they can use tool calls such as Google Search, and building on this, Gemini 2.5 integrates advanced reasoning, allowing it to interleave the search capabilities with internal thought to answer complex multi-op queries on long horizon tasks. They also mentioned that in terms of long context, Gemini 2.5 Pro is able to consistently recall a 1-second visual event out of a full 46-minute video. So this is a needle in the haystack benchmark, and this was also quite surprising to me. I was not aware of this. When it comes to multilinguality, which is not really interesting to most people, but anyways, they also improve this in Indic languages, Chinese, Japanese, and Korean languages. Then for audio, they integrate advanced capabilities such as thinking, affective dialogue, contextual awareness, and tool use into Gemini's native audio models. Video, which is pretty cool. How did they get to 3 hours? Well, in essence, what they did is that they reduced the number of tokens per frame from 258 to 66, which is a factor of 4, but somehow this only reduced the amount of hours, or this only increased the amount of hours that it can fit into the context window by 3. So maybe there's some overhead that is not considered in this calculation, but if you're not sure what visual tokens per frame is, in essence, since transformers are a sequence-to-sequence model, we need to create a sequence out of tokens, which essentially means creating patches of the video so that each pixel belongs to a sequence and then just feeding that to the transformer. So they reduced this from 258 to 66, which probably means that they just made the patches larger, but maybe they also did some other cool tricks to reduce the number of visual tokens per frame. An interesting educational result of their improved video modality is that, for example, you can create an interactive app, such as a quiz, to test students' understanding of a video from that video itself. So essentially, a teacher could upload a video, and then the students would have to answer questions of that based on their understanding. And then in terms of Gemini as an agent, there's of course deep research, which was quite big around February to March. In essence, the agent is optimized to perform task prioritization and is able to identify when it reaches a dead end when browsing. There's a typo here. And one thing that I was quite interested to see is that on the Humanity Last Score benchmark, they improved it from 7.95 to 32.4 with high compute in this month, based on deep research. This section is about the path to Gemini 2.5. They briefly mentioned that there was Gemini 2.0 Pro in February 2025 with a 2 million size context window. So that was, I guess, their largest context model they've ever released to date. And then they also had the image generation model, which had capabilities such as multi-step conversational editing or interleaved text image generation. I'd recommend going to Google AI Studio and trying out the conversational editing. It's pretty impressive. And then when it comes to Gemini 2.5 audio generation, the text-to-speech can generate speech with multiple speakers, which enables the creation of podcasts as used in Notebook LLM audio overviews, which I know everybody has heard of because nowadays, all of the AI slop is just Notebook LLM podcasts. And finally, they also offer an advanced thinking variant for their text-to-speech model that effectively handles more complex queries and provides more robust and reasoned responses in exchange for some additional latency. When it comes to DeepThink, this was just released recently, and it allows Gemini to creatively produce multiple hypotheses and carefully critique them before arriving at the final answer. So only trusted testers and advanced users have been able to access this, so I really can't say much about what this does, but let's move on to the next section. I will skip through all of the evaluation metrics because that is not interesting to me, and I'm probably sure it's not interesting to you either. They mentioned the Gemini 2.4 Pro playing Pokemon, and that was quite interesting. One thing worth noting is that whereas the initial model took 800 hours to complete, the second model, which had a improved agentic harness, which essentially means it was interacting with the game in a more efficient way, took essentially just half that time. So it went from 813 hours to 406.5, which once again is nearly exactly half the time of the first run. So quite an impressive improvement over just a few months. And then they do talk about some of the struggle points of 2.5 while playing Pokemon. And one thing worth noting is that the developer who made this independently essentially saw that during an ablation, when all vision was completely removed from the model context, the model was still able to function roughly as well as without the vision information, showing that most of the performance does not significantly depend on the visual input. Instead, it was just getting it from the game's RAM state. So to say that it's still not really multimodal, it's just reading the game's RAM and then acting based off of that. And furthermore, even though Gemini 2.5 Pro has a 1 million context window, as the context grew significantly beyond 100,000 tokens, in the Pokemon game, the agent was essentially repeating the preferred actions from its vast history rather than finding new plans. And therefore, teaching an agent to effectively plan and avoid such loops over these large trajectories is an exciting and active area of research. And now when we mention what else Gemini 2.5 can do, an interesting application which I saw in the report and I've highlighted here is that it can take a PDF script of a play such as Macbeth and then tell drama students how to best practice their lines or make a tool to do that. And another thing which I thought was amazing is that Gemini 2.5 Pro you can take a picture of a bookshelf and then it will make a curated book recommendation application based on those books. And another two examples which I thought were amazing, check out these sources, I checked them out, it was really amazing, honestly, were a interactive solar system model and drawing a logo using Fourier series. And this is all done with their most capable model 2.5 Pro. They also mentioned that it's integrated in many Google products. And then let's jump to the safety section, which most of it we're gonna skip. I don't say that I'm skipping it because safety isn't important. There are some sections which I'd like to highlight with you guys. The first one being memorization and privacy. So what is discoverable memorization? It is the case that LLM models are known to potentially produce near copies of some training examples. And then in this graph here, they show how much or how little the models memorize. So interestingly, GPT 2.5 Pro only memorizes 0.001% of its output data when they tested it. And what we have here is dark green is literally exact, like a word for word replication of the input data, and then approximate is like similar. And then this is just to say, did it reproduce the training data or not? And then on the right, it's saying, is the training data that it reproduced personal? Because when GPT-3 came out in November 2022, one massive problem was that you could literally get people's emails from it. So you can see here, for example, that with Gemini 2.5 Pro, the amount of personal data released is quite low. And in fact, it's not at all. So I just realized that yellow means no. So yes is only on the 1.5 models. So starting from Gemini 2, essentially no personal information was released in the model's output. But this is also according to Google, which doesn't have the best data privacy history in the world. So you may take this with a grain of salt. Now we're going to talk about the frontier safety framework and critical capability levels. So this is kind of saying, can it make a nuke? Can it make a infectious disease, etc. And in this graph here, they have the chemical, bio, I forget what this entire stands for, but pretty much like chemical methods, radiology, etc. And all they're saying is that it's not reach, it's not reach, it's not reach. So according to Google, this model is safe, nothing to worry about, but this only means that they're getting more capable because if you compare it to the previous models, then they are performing much better on these capability benchmarks as before, and better being a bad thing since it basically means they're getting better at like advising terrorists. In particular, when they asked the researchers what was happening, external researchers for chemical and biological risks said that the model outputs detailed information in some scenarios, which often provided accurate information around experimentation and problem solving. However, they found the steps they were too broad and high level to enable a malicious actor. And then for radiological and nuclear stuff, the external researchers found that the model responses within this domain were accurate, but lacked sufficient technical data to be actionable. And now we've pretty much reached the discussion section. So they say here that reflecting on the path of Gemini 2.5 has shown staggering performance improvement attained over the space of just 1 year. And this points to a new challenge in AI research, namely development of novel and sufficiently challenging evaluation benchmarks, because the current ones are struggling to keep pace with model capacity improvements, especially with the advent of reasoning models. Furthermore, not only are benchmarks starting to saturate quickly, but every new benchmark that gets created can end up being more expensive and take longer to create than its predecessor. One thing I did not know is that for the HLE benchmark, people were getting paid as much as $5,000 to provide questions. With this being said, I myself am working on a benchmark based on the game Factorio, which is not costly. So if you're interested in this, then please search up the Factorio learning environment. And in conclusion, they say, being able to scale evaluations in both their capability coverage and their difficulty, while also representing tasks that have an economic value, will be the key to unlocking the next generation of AI systems. So that was all for the Gemini 2.5 technical report. Let me know if you have any comments or questions.